So, let us now discuss the concept of conditional distribution of discrete random vectors. So, suppose omega p is a given probability space, and suppose x equal to x1, x2, xp is a p dimensional random variables. So, for the time being I am not assuming that it is discrete. So, it can be discrete or absolutely continuous, and suppose it has distribution function f x. So, first I talk about the conditional distribution function when it is given that x belongs to a given set D. So, let D be a subset of R p, and suppose this D is such that probability x belonging to D is positive. Then the conditional distribution function of x given that x belonging to D is defined by. So, I use this notation for conditional distribution of x given x belongs to D, which is same as probability x less than or equal to x given that x belonging to D. So, probability of A given B is same as probability of A intersection B, which is probability x less than or equal to x belonging to D divided by probability of B, which is probability x belonging to D. So, this is how we define the conditional distribution function of x given that x belonging to D. It can be checked that this is a proper distribution function. So, it satisfies all the properties of a distribution function in terms of variable x, and here D is a fixed set. So, that is given to you. So, that is how we define conditional distribution function of x given that x belongs to a given set T. Now, we will talk about conditional distribution function of x when y is given to be a fixed quantity, which just follows from the earlier definition. So, let x equal to x1, x2, xp, y is y1, y2, yq, and suppose z is x and y taken together. So, it becomes a p plus q dimensional random variable. Suppose Sz and Fz are the support and the probability mass function of z. Now, if z is discrete, then we know that marginal distribution function of x and y are discrete. So, let S phi and F phi respectively denote the support and joint PMF of phi. So, here I am assuming that z is a discrete random variable, because we are talking about its probability mass function Fz. So, its marginal distributions of x and y would also be discrete. So, that is why they would have a probability mass function. So, let S phi and F phi respectively denote the support and joint probability mass function of phi. So, I am talking about conditional distribution of function of x given y. So, for a fixed y belonging to S phi, define S of x given y as collection of all those x belonging to R p such that x y belongs to S z. So, this is for a fixed y. Then the conditional distribution function and conditional probability mass function of x given y is equal to y, where y is in S phi is fixed, are defined by f x phi x phi, which is same as probability x less than or equal to x given y is equal to y, which is same as probability x less than or equal to x, y is equal to y given probability y is equal to y. Now, note that since y is in S phi implies that probability that capital Y is equal to small y is positive. So, that is why this conditional probability is well defined. So, what is this? This can be written as union of singletons. So, which is same as collection of all those t belonging to S x given y, because S x given y was collection of all those x phi, collection of all those x such that x phi belong to S z. So, t belong to S x given y. So, that means, and t is less than or equal to x. So, I am summing over that, and f z t y. Probability y is equal to y is a marginal probability mass function of y, which you can get by summing out the unwanted variable x, which is t over here. So, I am summing out it over this, and summing it over collection of all those t such that t y belongs to S z. So, this is how you get the conditional distribution function. What would be the conditional probability mass function? F x phi given x phi, which is same as probability x equal to x given y is equal to y, which is same as probability x equal to x, y is equal to y divided by probability y is equal to y, which is same as joint PMF of x and y, which is f z x phi divided by marginal PMF of y at phi. Now, note that here y is in S x, y is in S phi. So, this would imply that f phi y, which is probability y is equal to y, is positive. So, this conditional probability mass function is well defined. So, we have talked about conditional distribution function f x given y, x given y for a fixed y, and this is a probability mass function. The question is this really a probability mass function corresponding to this distribution function or not? So, that is what we will see in this remark. So, the first thing is as I told you before, that it is easy to verify that the function f x t defined in above definition is a proper distribution function. That is, it satisfies the 4 properties of a distribution function. Then the second part of the remark, it is straightforward to establish that for every fixed y belonging to S y, the function f x y dot given y is a proper distribution function. And in fact, this is contained in this, because once you show this, this clearly follows. And one can also show that this probability mass function, which is a conditional probability mass function, is the probability mass function corresponding to this conditional distribution function. Straightforward to show. So, that one can take as a exercise, straightforward exercise. So, now we have defined the conditional probability mass function. So, conditional probability mass function is nothing but joint probability mass function divided by marginal of the fixed variable y. So, now let us see whether I can check independence through probability mass function or not, and this is what the next result says. So, let x equal to x 1 x 2 x p be a p dimensional discrete random variable with support S x and joint probability mass function f x. Let S x I and f x I denote the support and marginal PMF of x I is equal to 1 to p. Then it says x 1 x 2 x p are independent if and only if the joint probability mass function is same as the product of marginal probability mass functions. So, one can also use the probability mass function to check the independence. What one needs to do is, one needs to check whether joint PMF is same as product of marginals or not. And this is a necessary and sufficient condition for independence of random variables x 1 x 2 x p. Another easy consequence which we get is, if x 1 x 2 x p are independent, that implies that support of x has to be a cross product of supports of S x 1, S x 2 and S x p. So, let us try to say this. I will illustrate the proof for p is equal to 2. For general p, the proof is exactly on the similar lines, except that you will have to deal with slightly more complicated notations. So, suppose that 1 holds. So, that means 1 is that the joint probability mass function is same as the product of marginals. So, S x in that case is collection of all those x belonging to R 2 such that f x x is positive. But f x x is same as f x 1 x 1, f x 2 x 2. So, this is same as collection of all those x belonging to R 2 such that f x 1 x 1, f x 2 x 2 is positive. But f x 1 x 1 and f x 2 x 2 are already non-negative quantities because they are probability mass functions. So, the product of 2 non-negative quantities is positive. That would happen if and only if each of them is positive. So, that means collection of this same as collection of all those x 1 x 2 belonging to R 2 says that f x 1 x 1 is positive and f x 2 x 2 is positive. So, that is nothing but I look at the first coordinate, which is same as collection of all those x 1 such that f x 1 x 1 is positive, which is S x 1, cross collection of all those x 2 belonging to R such that f x 2 x 2 is positive, and then I take the cross product. So, what I observe is, if 1 holds, then S x is same as S x 1 cross S x 2. Now, to show that they are independent, I try to show that their joint distribution function is same as the product of marginals. So, for x is equal to x 1 x 2 belonging to R 2, f x 1 x 2 is same as probability x 1 less than or equal to x 1, x 2 less than or equal to x 2. So, this is same as t belonging to S x, t less than or equal to x, f x t. But this S x is same as S x 1 cross S x 2. So, what is t? T is nothing but t 1 t 2. So, t 1 t 2 belonging to S x 1 cross S x 2 is equivalent to saying that t 1 belongs to S x 1 and t 2 belongs to S x 2. So, this is same as saying that t 1 belongs to S x 1, t 2 belongs to S x 2. T less than or equal to x is equivalent to saying that t 1 less than or equal to x 1 and t 2 less than or equal to x 2. So, that means you see t 1 and t 2 have been separated out. So, this sum is basically a double sum, which is t 1 belonging to S x 1 and t 1 less than or equal to x 1. T 2 belongs to S x 2 and t 2 is less than or equal to x 2. So, there is no intermixing of t 1 and t 2 terms. They have been separated out because you could write S x as S x 1 cross S x 2. And then fxt is same as fx1 t1, fx2 t2 by our hypothesis. So, it becomes 2. So, what is happening is I have separated out t1 terms here and t2 terms over here, and they are sitting inside the summation sign. So, it looks like the summation sign also can be separated out, and that is what you do. So, let me go back to the next one. So, this is same as this, which now you can separate it out. So, this same as t1 belonging to sx1, t1 less than or equal to xx1, fx1 t1, then summation t2 belonging to sx2, t2 less than or equal to x2, fx2 t2, but this quantity is same as fx1 at the point x1, this quantity is same as fx2 at the point x2. So, what you get is joint distribution function of x1 x2 is same as the product of marginals. Sorry, this would be x1, this would be x2, which implies that x1 and x2 are independent. So, if one holds, that means if the product of if the joint probability mass function is product of marginals, then x1 and x2 are independent. Now, suppose that x1 and x2 are independent, also that joint probability mass function is same as product of marginals. So, x1 and x2 are independent, then by definition their joint distribution function is same as the product of marginals. I have to show that joint probability mass function is product of marginals. So, for x1 x2 belonging to R2, joint probability mass function fx x1 x2 is same as probability x1 is equal to x1, probability x2 is equal to x2. By the standard technique which we are doing so far, using the continuity of probability mass function, this is same as limit h going to 0, probability that x1 lies between x1 minus h to x1 and x2 lies between x2 minus h to x2, and I take h going to 0, because this would be same as I can make it here h, replace h by 1 by n, and I can take n going to infinity, then it would become intersection, and intersection would become probability x1 is equal to x1 and x2 is equal to x2. A standard argument which we have been using quite frequently. So, this is same as this probability. This is a probability of x lying in a rectangle, which we know is same as fx1 x2 minus fx1 x1 minus h x2 fx x1 x2 minus h fx x1 minus h and x2 minus h. So, this is when 0 of them are the first argument. So, both of them are second. So, x1 and x2. This is the situation when one of them is the first argument. So, first argument could be x1 minus h, then here x2 minus x1 times x2 minus h. This is the situation where both the arguments are the first argument. Okay, so, this is same as fx1 x1 fx2 x2 by this condition. This is same as fx1 x1 minus h fx2 x2 minus this is same as fx1 x1 fx2 x2 minus h. This becomes plus fx1 x1 minus h fx2 x2 minus h. When I take h going to 0 in each of them, this becomes x1 minus fx1 x1 minus, limit h going to 0 of this quantity would be fx2 x2 minus, limit h going to 0 of this quantity would be fx1 x1 minus fx2 x2 minus. So, this becomes fx1 x1 x2 fx1 x1 minus fx2 fx1 x1 x2 minus plus fx1 x1 minus fx2 x2 minus. So, I take things common. So, here I take fx2 x2 common, then it becomes fx1 x1 minus fx1 x1 minus. Then here I take minus fx2 x2 minus, then it becomes again fx1 x1 minus fx1 x1 minus fx1 x1 minus. So, combining this, I get this quantity fx1 x1 minus fx1 x1 minus multiplied by fx2 x2 minus fx2 x2 minus. But this quantity is same as probability x1 is equal to x1, which is same as fx1 x1. This quantity is same as probability x2 is equal to x2, which is same as fx2 x2. So, the given condition is satisfied. So, what we saw is if you have to check the independence, you look at the joint PMF and check whether the joint PMF is same as the product of marginals or not. The proof of the second proposition that Sx is equal to Sx1 cross Sx2 in fact is contained in the proof of the last part, because if x1 x2 are independent, then you know that fx x1 x2 is same as fx1 x1 fx2 x2. and if this happens, we have seen that Sx is same as Sx1 cross Sx2. So, one can easily check whether Sx is same as Sx1 or Sx2 or not. If this does not hold, one can directly conclude that x1 and x2 cannot be independent. So, one way to check independence or to rule out the independence would be look at the support of the joint distribution. If in that the terms of x1 and x2 cannot be separated out, then that would give an evidence that the components of random vector x1 and x2 are not independent. So, this last result can be easily extended to the situation where you are dealing with random vectors rather than random variables. So, let us do this result. Let x1, x2, xp be discrete random vectors of possibly different dimensions. Then x1, x2, xp are independent if and only if the joint occurrences of x1, x2, xp in events in sets a1, a2, ap is same as the product of individual probabilities. These are if and only if conditions. Then one can easily prove that x1, x2, xp are independent if and only if there any functions are independent. So, that means psi1 x1, psi2 x2, psi p xp are independent for any function psi1, psi2, psi p. So, what it suggests is functions of independent random variables are independent. So, I will not prove it, it is a straightforward, although the proof may be tedious, but the idea of the proof is simple. So, this is what it says, that the first result where we talk about the random variables x1, x2, xp are independent if and only if the joint probability mass function is product of marginals, that has its analog for random vectors also. So, that means if you have random vectors x1, x2, xp, which may be possibly of different dimensions, then they would be independent if and only if you look at the joint PMF of the random vectors x1, x2, xp is same as the product of marginal probability mass function of x1, x2 and xp. Another thing worth noting over here, it's random vectors x and y are independent if and only if the conditional distribution function is same as the unconditional distribution function of x. So, that means conditional distribution function of x given y is same as the unconditional distribution function of x, which is equivalent to saying that conditional probability mass function of x given y is same as the unconditional probability mass function of x. That follows from the fact, because for example, f x given y, x given y is same as f x x for y belonging to S y. So, that this probability mass function is defined if and only if f x y x y divided by f y y is same as f x x, which is same as f x y x y is same as f x x into f y y. So, in fact, this condition is equivalent to saying that the joint probability mass function of random vectors x and y is same as product of marginal probability mass functions of x and y, and which is equivalent to saying that x and y are independent. So, what we conclude is random vectors x and y are independent if and only if the conditional probability mass function is same as unconditional probability mass function. And that in a sense justifies the way we have defined the independence. What it says is, given the information that y is fixed at small y, the distribution of x remains unaltered. So, that means the conditional distribution given this information that y is equal to y is same as the unconditional distribution. So, in a sense the y does not affect the occurrence of x, and that justifies the way we have defined the independence, that is the joint probability mass function is same as the product of marginals. Now, that condition is also equivalent to say this follows exactly on the same lines. So, which I leave. So, now I go to the next slide, which tells you another way to check independence.